So, in the last lecture on Bitonic sort, we have been discussing about the recursive structure. So, what we identified was that step 1 in the Bitonic sort is nothing but application of smaller instances of step 2 and then combining them to create the step 1, right. And the next thing was we are trying to figure out what is the step 2. And if you just recall from our further discussions, we figured that the Bitonic sort algorithm can be broken into 2 parts. So, you apply Bitonic sort on the smaller parts, you break the total input into 2 parts, apply Bitonic sort ascending followed by Bitonic sort descending on the first part and the second part respectively to generate a Bitonic sequence, and then apply the Bitonic merge, which is essentially your definition of step 2, right. So, these first 2 steps generate the Bitonic sequence, then you apply Bitonic merge, that is the step 2, right. And so, the point we are trying to make now is that okay, what is step 2 or what is the fundamental behind the Bitonic merge process. Now, when we went back to our example here, we figured that in the Bitonic merge essentially what we have is a sequence of comparisons, as we can see. So, if the input size is 8, we are applying 4 comparisons here on strides of size 4. So, half of the size, right. So, this sequence of comparisons are followed by smaller instances of Bitonic merge, that is the important thing. Now, if you look into these parts, so we have a sequence of 4 comparisons, then a set of steps. Now, if you look into these parts, I can say that the overall thing is a Bitonic merge of size 8, and these 2 are nothing but Bitonic merge of size 4, right. So, from this recursive structure we can say that the merge step can again be written as a sequence of comparisons followed by 2 calls to Bitonic merge on a reduced set, right. With this understanding, if we look into the program here, the pseudo code here, so you have this Bitonic merge with a low and a high, and you are given the direction. So, essentially now what will happen is you will make those sequence of comparisons, then make the call, 2 calls to be precise, as we saw for this part and this part, you are making 2 calls, but the calls are going to happen on 2 separate parts on the half sized inputs. So, from low to m equal to n by 2, the high by 2, and then for the rest half. What is important is to understand is the merge process, the direction is same, right. So, in these 3 calls, in all the comparisons and in all the merge calls, the direction remains same. Again, I will repeat, in all the comparisons and in the merge process, the direction remains same. If you look in here, that's true, right. The direction is same as the desired merge process direction of the outer call. So, here the outer call is expecting a Bitonic sequence as input and is going to provide an ascending output, right. So, for that we make a call to merge of size 8 with ascending output direction, and here we do the comparisons in that direction, and for the sub calls to the smaller merge process, again the direction does not change, right. So, this is the most important thing to identify with respect to step 2, that I can simply write the merge process recursively like this. All we need to do, we will have first this set of comparisons. The comparisons are happening with a half size stride. So, from the start value you make comparisons up to the midpoint, right, low plus m, that is the midpoint. As you can see, from the start you are making comparisons 1, 2, 3, 4 up to the midpoint. Each of the comparisons are considering this data with a data at the stride size which is half of the overall width of the data, right. So, you are comparing the ith value with the I plus mth value. Now, this m is the stride size and the stride size is again equal to n by 2. So, half of the data width, as I have been saying, right. So, I hope this is now clear to you that we have a sequence of comparisons here, and these comparisons will have their stride as defined, and then after the comparisons we just make calls to two consecutive Bitonic merge, right? So once we execute this overall program, we have the Bitonic sort done, right? But now the question is, what about the CUDA implementation? So first thing we have to figure out is, okay, let's have a look what are the parallelizations. So as we can see, the sorting network provides me the view that with respect to at the same time point what are the operations happening. So these are the operations that are happening in concurrently, and here again these are the operations which have no dependency and I can make them happen concurrently, right? So in red we are trying to figure out which are the concurrent operations that we have, and as we can see there are a lot of concurrencies present inside each stage. So first I have step 1. Inside step 1 I have two parts, right? So first I have these single comparators, and then I have this idea of again applying the step 2 in a larger context, and then again applying the bigger merge process here, right? So I hope this is clear that why even inside step 1 I am using two different colors, right? So the first part essentially tells me applying step 2 in the smallest contexts, and then here you are applying two instances of step 2 in a relatively large context, and then you are applying step 2 in the bigger possible context here, right? So looking at the parallelization, as we can see, I can define the per thread activity like this, right? So I can run these parallel threads, right? And each thread in this part of the computation of step 1, they can perform these comparisons in parallel. So I would require 4 threads here, half the number of threads as the number of data points. So each thread can perform 2 loads and then do the comparisons, put the values in the shared memory, right? And then the threads can just do a sync thread here, progress here, effectively do these comparisons, and then progress, so on and so forth, right? So overall we can summarize like this, that associate every CUDA thread block with a sorting subproblem. So essentially if we have a significantly large sized array to sort, you define CUDA thread blocks for each of the subarrays, and then you apply the merge on the result of the on the results for the different thread blocks that you derive. So at the end you have to actually merge results from each of the SMs and solve the original sorting problem. So fundamentally we need to also identify that what is the size of the thread block, as we discussed that since 4 threads are going to do the job in this case. So if I have an 8 element input, I would require half the number of threads. Okay, but what is the shared memory size? Is going to be same as the input size here for each block, right? So it's going to be twice of the number of threads, right? Now these are simple codes that we have taken from NVIDIA CUDA SDK benchmarks, right? And so first thing we highlight here is the comparators code. So what we have is two inputs. Now we are writing a general situation here. So we have 2 inputs with key value pairs, right? We have 2 inputs with key value pairs, and we also provide a direction. And then for the inputs we compare the key, and then we compare it with the direction. Now as you can see that the idea of this program is similar to the C program comparator that we had. So essentially we are checking it with the direction. If I is greater than j, and that's the true case, then we do the exchange. So we are considering downward arrowed sorting networks by this example here. And of course if the direction is otherwise, then it will represent the upward arrow sorting network, right? So as we derived earlier, considering dir as 1, I have this. Considering dir as 0, I have the reverse, right? So we compare the key, and then we compare we just compare the result of this comparison, positive, I mean 1 or 0, with the direction, and accordingly we decide to swap the key and swap the value, right. So this is just an extension of the original comparator circuit considering key value pairs. So we are going to do the sorting based on the key values. Now we provide the implementation of Bitonic sort on shared memory. So we will have each thread loading 2 values to the shared memory and proceeding through the different stages of the sort. So we define 2 of these shared memory segments, one for the storing the key values and one for storing the keys and one for storing the values here. And then we have to figure out what is the per thread activity. That means we need to figure out, okay, each thread is going to load and store 2 key value pairs. So they are going to work in which area of the memory. So for the 2 threads, the first thing you do is you calculate the offset to the beginning of the sub array. That means inside which of these blocks a thread is going to do the load activity, right. It has to identify that. So what we do is we check the block ID. So whatever is the block ID, we are considering x dimensional, 1 dimensional data here. So you just multiply the block ID in the x direction with the shared size, and then if you do a plus thread ID x dot x, you get the offset, right. That means inside the shared memory corresponding to this thread block, what is the offsetted location in the shared memory where this thread is going to load the key, load the value, and also the other key and the other value. We just call them as destination and source key values, right. So this part of the code actually performs the computation of that offset. So this is a block, and you just compute the offsets of the key value pairs, right, because you are considering for each block you have 2 shared memories. So every thread is going to load 2 of these keys and 2 of these values. I mean, considering only 1 dimensional data here, right. So once we have figured out that this is the location from which we are considering the threads to load the values into the shared memory. So now the pointers have been shifted to the offsets. So now you can just access the location with this as the base shifted by 0 for the source key and the source value, right, and you write it back to the shared memory's location only with the thread ID x offset. I hope this is clear. As we can remember that each shared memory is being defined in a per block basis, right. Each shared memory segment that we have here is there in a per block basis. So first each thread figured out in the global memory what is the offset or what from where it is going to load the data, is going to load 2 of the data points, right, and then it figured out using the thread ID based offset into the shared memory that where the locations they are going to write, right. So this is my shared memory. From the global memory I have figured out what is the data I will write, and then in the shared memory for this block, just by using the thread ID x based offset, I am figuring out per thread block this is the location where I am going to write the key, and so this is the shared memory for keys, and similarly I have the shared memory for values. So in that I will also figure out where to write the value, and so on and so forth. Now as we see that every thread is going to do 2 loads to the shared memory, both for threads and values. So the second load has to happen at a stride with an offset of shared size by 2, right, because it has first figured out its location, the base location where it is going to load using thread ID x inside the shared memory block, and then you add that thread ID x with half size of the shared memory block to figure out what is the other location where also is going to load the key, right? And that is guessed from this dsource key. And similarly, how do I get the load data address from the global memory? Well, I have already shifted this to this dsource key is now pointing to the location from where you have to just load the first data point, right? So that's why you can access it by index 0. So you can just put the index as shared size by 2, and that would give me the other location in the global memory from where I am going to load the second data point, right? So just right. So this is the second location from where I am going to load the other data point. So first thing we did was we calculated the offsets. That means what is the location in the shared memory where I am going to load the data, right? And then we just loaded the keys and the values at the respective locations with the offsets as provided. Now we come to the second phase, that now I have just figured out that where the loads are going to happen in the shared memory by the thread, and each thread is just doing the 2 loads from the global memory to the shared memory. The next thing that is supposed to happen is we are going to enter the step 1, right? We are going to enter into the step 1, in which we are going to build in parallel the Bitonic sequence, followed by in step 2 we are going to figure out how this Bitonic sequence is going to be arranged in the completely ascending or descending order, right? As we have seen from our earlier algorithm that well, all that we will be needing to do is we will first have the sequence in the step 1 and step 2. So here first we show the part for the Bitonic merge here that's happening for the different segments that are going on, because we have already identified that even for step 1 we just need to carry out the Bitonic merge process at the different segments that are there of the program, right? Sorry. So before carrying out any of these comparisons, we need to figure out that what should be the direction of the comparison, and of course what should be the positions where the comparison operation has to be performed, right? So for that we introduce 2 variables here. This variable ddd is kind of computing what is the direction, and this variable pos is trying to figure out what is the position where the comparison has to be performed, right? Now if you have a look into the sequence of operations that we do here, right? So let's try and figure out that how to assign these comparisons in as a per thread activity, because till now whatever we have done is to figure out how each of these 4 threads are going to load the values, right? So the next phase is to figure out how each thread is going to be orchestrating the comparisons that are to be done. So what we do is, okay, for performing the comparisons, we let thread 1 do the first comparison, right? And then we let thread 2 to do the second comparison, and then we let thread 3 do the third comparison and thread 4 does the other comparison, right? Or maybe I can just use the actual IDs of the threads, which would be 0, 1, 2, 3. Right. So, these are the per thread activities, and then coming to the next part, what we do is in the next phase of operations. So, if you may recall, this entirely is my step 1. Inside step 1, I am essentially executing step 2 first with a 1/4 of the input size, and then I am executing step 2 again with half of the input size, right. So, here this is my definition of the per thread activity, and then I have this is the part that would be done by thread 0, and then this is what will be done by thread 1, and we will have the following 2 done by thread 2 and thread 3 respectively, so and so forth, right. So, as you can see, what is happening is in the first part we have threads doing the comparisons at a specific location, and the next thread is doing the comparison at another location with the direction continuously flipping, right. Then when we come to the next part, what we have is the threads again doing the comparisons at a bigger stride. For 2 threads the directions do not change, and again for 2 threads the direction do not change, right. So, somehow we need to figure out that how this effect can be brought in, right. So, for that, if you check, the way we are actually computing the direction is basically a function of the thread ID and the size value, right. So, we put a for loop here which is trying to figure out that okay, in which stage we are operating of step 1, right. So, let me just reproduce the picture here. We are just elaborating on step 1 here, right, and as we see that step 1 has 2 parts. So, this is the full picture of step 1. Now, since I am working with an 8 size input, in step 1 we have already figured out that what we do is here we run step 2 on half the size. So, I can just write this is step 2 on half the size here, and similarly step 2 on half the size here, and then we run step 2 on 1/4 of the size 4 times, right. So, essentially I can say the number of times I am running step 2 is going to be controlled by the outer loop, and inside each iteration of the outer loop I am doing the number of comparisons which is controlled by the inner loop. I hope this is fine. So, the number again I will repeat. So, the number of phases I would say of applying step 2 in different stride size is being controlled by the outer loop. For example, here you are executing step 1 on an input of size 8, right. For that you have to execute step 2 on half the sized input twice, and step 2 on 1/4 the size of input 4 times, right. The fact that you are going to use step 2 in 2 different configurations is being reflected by the outer loop, right. So, the outer loop is controlling in what configuration I am going to apply step 2. First, when I run the outer loop, it's setting the size variable at 2, and it is saying that okay, you are going to apply step 2 with the comparisons done between two consecutive elements. Okay, and that the fact that these comparisons will be done, so essentially you are applying step 2 by 4. That means you are going to apply step 2 on input of size by 4 times. Essentially you will be doing 4 number of comparisons. That is going to be controlled by the inner loop. Look at the next iteration of the outer loop. You are increasing size by 2. Once you increase size by 2, what's happening is, again I will just repeat, once you increase size by 2, what's happening is you are reconfiguring your way of running step 2, and you are saying that okay, now I will be I will not be comparing I am going to run step 2 again at a configuration where it is input size divided by 2, and that is realized again by the inner loop with suitable choice of size and direction. So if I just look that how the values of size and stride are changing. So initially when I start, well, I have size equal to 2 and stride as 1, and so with that configuration, since stride is okay, by the way, the stride is computed here, and that comes out to be 1 because size is equal to 2, and all we are doing is we are just running the inner loop, and in each iteration of the inner loop we are actually going to increase this value of stride, right. Starting from the initial value, right. So what we have here is we start with size is 2. So when we figure out that okay, in that case stride would be 1. Now since stride would be 1, I would get in here, and here I am going to execute the comparison operation by all the 4 threads, right. So I will execute 4 different comparisons, right. So they are all done in one shot by the 4 threads in parallel, and then I am trying to decrease the size, right. So that would mean, since this is an integer variable, stride was already 2, stride was already 1. If I decrease by halving it with 2, it goes to 0 and the loop doesn't execute anymore, right. So in that way I have this one iteration of the loop, and inside this one iteration of the loop I have all the threads executing one comparison. In that way I get 4 of the comparisons done in parallel, and the comparisons are done on adjacent values. This is dictated by the stride variable, and the size value was set to be 2, right. So now in the next iteration, when I come back for the outer loop, I would have size has increased by this factor of 2, right, because of this left shift, but still it's small than the shared size. So I come to the other part of the step 1, and here I am now going to execute these 2 different parts of step 2, one for for half the input size, one here and the other here. Let's look at how this is now getting realized. So now I have set the size value as 4, right. Since size value has been set as 4, I am now going to execute with stride at 2, because stride is size by 2, and then again the loop will again execute with a stride value of 1, and then the stride will go to 1 go to 0, and it won't execute anymore, right. So when I execute with size as 4 and stride as 2, let's see what's happened. Okay, again I will get into this loop, and all the threads will execute comparison, but now the comparisons are going to happen with the stride of 2, right. That's why you get these 4 comparisons happening at a larger stride size. I mean, pardon my picture, and maybe we look at the original picture. So, I am talking about these 4 comparisons here, right. As you can see, they are happening with a stride size of 2. Yeah, and then in the next iteration of this loop, well, I will again enter into the next iteration, because I will half the stride, that will become 1, which is still greater than 0. So, now I will again perform 4 of these comparisons on adjacent data points, right. And their directions would be like this. So, this loop ran with for 1 iteration in the first size. Essentially, it executed 4 different comparisons. Essentially, all of them were the atomic instances of step 2 running on 1/4 the size of input, that is the step 2 by 4 that I am trying to say. So, essentially, and that covers all the 8 inputs, right, in 4 pairs. Here again I am running it, I am just repeating. So, step 2 by 2 sized, that means step 2 on the input size of 4, that is right, 2 of the instances. And the way it is being realized is that, well, we set the size variable again now as 4, and with the size variable as 4, we get 2 possible stride values. That is why this inner loop is now going to iterate twice. In the first iteration, is going to perform 4 comparisons. In the next comparison, again 4 comparisons in the next iteration. In the first iteration, the comparisons are at strides of 2. In the next iteration, the comparisons are going to happen at strides of 1, right. So, in that way, this code is actually achieving the overall idea of performing the stage 1 or step 1 of the Bitonic sort. Now, observe the different ways the directions have changed. So, as you can see here, the direction was we have repeated, I am just repeating this, direction was continuously switching. In the next stage, the direction remained same for the first 2 threads and then switched for the next 2 threads, and that pattern continued here. To realize this switching activity of the direction, we do a bitwise AND based realization of this value using thread ID and size. If you can check these values here, you will see that how this expression is actually able to reproduce this idea of direction switch, where when I set the size as 2, the direction switches very frequently. When I set the size as 4, the direction switches for 2 threads. I mean, the first 2 threads have the same direction and the next 2 threads have the other direction. That is how the direction switch activity happens. And then for the position, again I have this expression which actually takes care of identifying for each thread ID what is the starting position, right. Because for thread ID 1, this has to be the starting position. For thread ID 2, this followed by there is a switch in the starting position. Yeah, so this is also something interesting. The comparison positions for each of the threads. This is for thread ID 0, right. For the next thread, the starting positions actually change. These are the starting positions for the next thread, and for the other threads, for the thread with ID 2, again it's this, and for the other thread it's this, right. So, these are the different starting positions that we have. Now, to achieve this sequence of positions as a function of the thread IDs, we use this access expression, right. So, I mean, you will need to check how this actually reflects those switches of position by the thread IDs. Now, This is also an example through which you can identify how everything is going on. So here we have actually noted down as a per thread activity that thread ID 0 is performing these operations, thread ID 1 is performing these comparisons, thread ID 2 is performing these comparisons, thread ID 3 is again performing these comparisons, so on and so forth. And we have also done some example computations of triple D position, position per stride, etc. Yes. Now we come to the other part of the code where we are kind of trying to figure out what is the step 2 here, right? So if you see in the step 2, you have this uint, which is basically the direction, right? Now in step 2, first of all, the important thing is we already have figured this out, that the direction doesn't really change, right? So you compute the direction and it just remains the same, right? So and then the thing that keeps on changing is at what stride value you keep on performing the comparisons, right? So maybe we'll take this up in the next lecture, and with this we'll end the current lecture. Thank you.